Hi, and welcome to the lesson about different states you may have. So, different state store are not only different aspects, different implementations you can use in stateful processing, you can also have two different state algorithms, the incremental and the full state algorithms, to be more precise. And unfortunately, there is no size fits all solution to our data engineering problems. Neither there is a no size fits all state solution. Because in some computations, you will need to store the whole state or a quite big amount of state records, whereas for the others, you will just need to have a scalar value. Like, for example, if you are doing the counter from our previous lessons, well, you just need to store the current count. When you want to do, for example, some, I don't know, maybe unique distinct count, well, then you will need to store either the ID of already processed records or you use some approximative approach like with Bloom filters. So you can see that there's already two different implementations for apparently the same problem, so the count of elements. And I will just give you a much more detailed example and explanation of these two different state algorithms in this lesson. And there are these two big, I would say, state algorithms categories, incremental and full. So the main difference between them is that one is memory efficient, but not that universal like the other, namely the full. So the full, generally you can use it everywhere to cover all use cases. Incremental is only reduced to some specific scope of problems. And what is this scope of problems? And let's understand these two approaches by starting with some kind of naive method for generating an average for the events processed so far. So here we have three input values. We have a state store, so in the state store we store these three values, and later we have our business logic that it's a kind of a division between all rows from the state, the sum of values by the number of rows. So far we have 3 rows, which is not a lot, but when you see the other micro batch, other processing, would say execution slot, well, you have 3 other values, and the state, of course, increases, and we can call it a state explosion because remember, streaming jobs are long-running jobs. They don't stop, if you see what I mean. So at some point you will reach your hardware limits and your state will simply blow up your cluster. And with incremental state store method, there is something much more smarter you can do. And I think that with this example, you will understand why we can apply it only to some specific use cases. So again, we want to compute the average, but here instead of storing all rows one by one, we simply store 2 values. So the first one is the sum. So we generate the sum as a kind of pre-processing step before writing data to the state store. And another, which is the count, which is also a kind of pre-processing step before writing, that just simply counts the number of records we have to process in the given execution. And here we will have a constant number of rows. We will every time have only 2 rows, one for the sum and another for the count. And it's memory efficient, but as you can see, it will not apply everywhere. Typically, you will find it applied to a lot of aggregations, like for example here for the average, but you can also use it for the sum, count, max, mean, other things that you can combine just by reducing the initial data set. But there is a drawback. So by reducing this state to some kind of scalar values, you lose what we could call the late data management, because when you have you might have the logic including some timestamp processing, and when you just reduce your input value to some numbers, to some aggregates without this time concept, well, of course you will lose the possibility to integrate this late or to manage late data easily. But do not consider it as something that will happen every time though, because as I said, it will always depend on your state to compute, and maybe sometimes you don't simply need to you won't simply need to access this late data until integrated in some special way, and in that case the incremental state will be fine. But just keep in mind that incremental state reduces the input data to some aggregated form, and this form may not be always appropriate for this late data integration. And again, to give you a picture and better understand the difference between stateful and incremental state, I will try to implement the user session navigation scenario, so the sessionization problem, with the incremental state store method. So here the logic is quite simple. I have pairs of page and visit time, and I will just show you what happens here if we use the incremental state store method. So we have this, we emit all three results, and later we keep only the last row from this micro batch. And already you can see that it will be kind of incremental session, so we will lose the possibility to emit it once in the end of user navigation, but that's not the problem. The problem is different, because here, remember, we emitted events, visits for 10 o'clock, 10:01, and 10:04, and we store just the last value in the state store. So the state size is under control, doesn't it? Yes, but there is some drawback. As you can see here, we got data for 9:58. And now we emit this. And if our downstream customers are not able to deal with this disorder, so because they just to give you the context, they think that the most recent data is for 10:04, whereas you can see here that you are sending them late data for 9:58. And if they can't deal with that case, well, yeah, it's kind of tricky to use the incremental state algorithm for this user session navigation problem. Whereas, so state is under control again, but there is an inconsistent result. But when you use the full state method here, so we have this, and we accumulate the user visit statistics in our state store, well, there is the state explosion, right? But when it comes to integrate the late data, so the 9:58, of course, you can see we store all states in append only mode, but once you decide to emit the final user navigation session, you can order these values and simplify a lot the data reading, because yes, you will be, of course, be able to put 9:58 before 10 o'clock. So as I said, it's a much more universal method because it covers probably all scenarios you can imagine. The drawback is that the state can go really big if you don't control it, if you don't have any retention period. So for example, here we store all state for the visits, but we could assume that, well, if the difference between the first record and the last record is like 10 minutes, when you can say, okay, I will flush all records I have before, so that before most recent record minus 10 minutes, so that you will reduce the size and the amount of data in your state store, and maybe have a much more safety, because it will be, there is still a risk that it will explode because it's still on the hardware, on the RAM memory, but the risk will be a bit lower. And that's the final outcome. Of course, you can order the values as you wish. And yes, I think that I gave you two, for me, self-explanatory examples of these two different stateful algorithms. So remember, incremental is reduced to the scope of problems you can present in kind of intermediary format, like for example all aggregates, whereas the full state has much broader coverage. It covers much more use cases, but with the drawback of having much more state to store in the state store and having this I/O impact even stronger. Thanks for watching and see you in the next lesson.